Welcome to Hydrology, Measuring Rainfall, Chapter 4, Lecture 1. I'm Dr. Marty Matlock. Let's get started. Precipitation, mostly rainfall for us, not snow, sleet, hail, but just rainfall. Events are generated by atmospheric conditions, as we've discussed in previous lectures. Remember this as we talk about rainfall, precipitation, and measurement, that these are physical phenomena driven by processes that we understand. Water vapor rises from the land surface to the ocean surface. As it rises into the cooler atmosphere, droplets form by nucleation, condensation of tiny vapor on tiny solid particles called aerosols. These droplets increase in size by condensation. Droplets become heavy enough to fall, usually 0.1 millimeter diameter. Then many droplets decrease in size by evaporation in the clouds. You have this circulation, and they rise back up again by condensation. Some droplets increase in size by impact and aggregation. Then large droplets can break up if there's enough uplift from less than 3 to 5 millimeters until they reach about 1.1 to 3 millimeters, and in some cases big drops, 5 millimeters in diameter, and they drop to the surface. This is the process of precipitation. It is a known process that is well understood and driven by atmospheric conditions across the landscape. Rain is powerful as it falls. Water is dense. Remember that 1 cubic centimeter of water is 1 kilogram, 1 liter of water, and it weighs a kilogram. It's heavy. A large raindrop, 5 to 8 millimeters in diameter, has a terminal velocity of about 10 meters per second. So it's falling fast, 30 feet per second. A large raindrop, 5 to 8 millimeters in diameter, has a mass of about 65 milligrams. Now, that single mass is not that great. It hits the Earth with about 0.000065 kilograms, which is 65 milligrams, per meter second force. That's 65 milligrams times 10 meters per second. For heavy rain, 50 millimeters per minute, every square meter of Earth is impacted by 900 drops per minute, or about 15 drops per second. That's a lot of force over time. And what does it hit? Well, as rain falls, it can hit the bare soil, it can hit rooftops, it can hit parking lots, it can hit vegetation, or it can hit water. Those are kind of the options it's limited to. When it hits vegetation, trees intercept the water. And there are a couple of things that happen. The trees intercept the water and the velocity drops, and eventually it breaks through, or it actually stays on the vegetation and evaporates from the vegetation back up. So you have this interception by the tree canopy or vegetative canopy. Think really small trees, grass and shrubs on the landscape, or crops across the land. That's a significant reduction of the force of rainfall on Earth. If we want to see what this looks like, raindrop impact on a sandy surface. This is a cool video produced by our folks at University of Minnesota. That impact is significant. These are small glass beads, but notice this impact. It displaces and splashes soil, and it creates a crater of impact where the water surface hits. Notice the surface tension about those glass beads, which it does the same with soil. 3.3 meters per second, that's a significant impact. So the raindrop hitting plants, as it comes down and hits a tree, you actually get a funneling effect in some cases. So the force of the falling raindrop hits the tree and funnels down the stems and the branches and funnels to the tree canopy and the system below. This is actually an interesting evolutionary adaptation of trees to harvest water, because that water funnels down the trunk into the root zone. So trees are not only expanding their leaf mass in order to capture more sunlight and compete for their neighboring plants for sunlight, they're competing for water. All plants do the same sort of thing. The way we measure precipitation is with rain gauges. USGS, NOAA, other National Weather Service, and others have rain gauges set up all across the United States in fairly high densities. And we capture rain coming through, dropping down into these tipping bucket rain gauges, which measure the rain in increments. And in this case, you see a computation of rainfall depth and intensity at a particular point, like this rain gauge, at 5-minute intervals. So at 5 minutes, you get 0.02 inches of rain. And then at 10 minutes, you get 0.34 inches of rain, or 0.34, which cumulatively is 0.36. And I just added up. At 15 minutes, you get another 0.1 inches, which becomes cumulatively 0.46 inches. This is not complicated. You're just adding these up as each increment of time passes. Now, if you're interested in 30-minute totals, you start totaling at 30 minutes. And at 30 minutes, you have 1.17 inches. And at an hour, you have 3.81 inches. And so forth. At 10 hours, you have 8.13 inches. And this is the way we calculate rainfall cumulative depth and intensity in inches per hour. It's not that complicated. These tipping buckets are fairly simple devices. They have an area where rainfall enters an orifice. That's a surface area. It has a debris filtering screen and a funnel which drops to this tube hole to this tipping bucket, which tips one way or the other. And every time it tips, it generates a measurement of mass using these load cells within the bucket, which weigh the weight of the bucket. And this information is then aggregated, and then through a number of electronic transmission systems, is collected and transmitted to a central location for processing. We have only in the last 15 years really expanded this mesonet or meso-density network of rainfall collections across the United States at fairly high resolution, which means we have a lot of areas that have 10 years of record, 15 years of record, but very few areas that have 100 years of record. Those are usually associated with airports or with research institutions or with other major sites. A hyeta graph means a rainfall graph from the Greek hyetos, which means rain. So it's a rain graph. That's what a hyeta means. An incremental hyeta graph is a bar chart of increments of rainfall for a specific time duration. Again, think about that previous data. If we look at time in minutes, if we look at time steps, 5-minute intervals of incremental rainfall in inches, we see this sort of effect of increasing rainfall. And we can plot that as a cumulative rainfall event, just as we saw in the spreadsheet. We can graph the cumulative rainfall over time. That's the cumulative rainfall over time gives us the storm pattern for that system. Now, the typical measure of rainfall is a 24-hour event. How much does it rain in a 24-hour event? Rarely does it rain for 24 hours in a location. Most of the times we have a much more intensive rainfall over a shorter period of time. Sometimes we'll have drizzle at the beginning and end of that, but most of the time the rainfall occurs in more of an intensive period of falling, and it's very highly variable, as you can see from this hyeta graph. Understanding our rainfall patterns are critical for predicting what happens to that rainfall in our mass balance approach to water in a watershed or catchment. We're concerned about 3 characteristics of precipitation events: intensity, frequency, and duration, as we talked about in the previous lecture. Intensity is the amount of precipitation that occurs at a location in a designated amount of time, duration. Frequency is the average number of times an event greater than a specific intensity occurs over time. And duration is the length of time, t, for which the storm event intensity is measured: 15 minutes, 1 hour, 12 hours, 24 hours, month, or year. We typically measure storm events in a 24-hour frequency. How much does it rain in a 24-hour period? Intensity, duration, frequency curves characterize the precipitation of an event at a location. Knowing the frequency of an event of a given intensity and duration allows the hydrologist to design for those events. Remember, we have our 5 cases. And remember, almost always we're in case 5 where we have no records in the vicinity of the location of interest. But we have to understand how to measure rainfall based upon the other 4 cases. which are increasing levels of periods of record and increasing geographic proximity to our sites of concern. The depth of an event, D, measured in a length unit, typically millimeters or inches, is the product of the intensity, length over time, millimeters per hour, inches per 15 minutes, and the frequency T. D equals IT. Data for precipitation IDF charts are for a location are readily available in the U.S., though not necessarily in other countries. So if you go to the NOAA PFDS website, which I've linked here, again, you've seen this before, you can zoom into the map very close and you can put your crossbar at a really close location. And you notice the green boxes, these are the rain gauges we have in the area. And based on where you put these crosshairs, it will interpolate based upon geospatial weighting, both the data and the graphical representation of precipitation depth and duration for recurrence of intervals, or precipitation depth and recurrence intervals for particular durations for you. There was a time when we had to do this manually by ourselves, as we've discussed previously. You don't have to do that now. As we look at NOAA's data sets, we also have national temperature and precipitation maps, which give us regional information from a national, regional, statewide, and divisional precipitation ranks based upon this sort of data collected at these rain gauge stations. And what you're seeing here are actual relative humidity and wind instruments for collecting other atmospheric information rather than just rainfall. That's why I have the shields on top of them. We're collecting all of this data at fairly high frequency automatically across the nation at a number of gauging stations. And you can select the kind of information you want, the parameters you want, and the area of coverage, CONUS or Alaska. Hawaii is a little weird. You have to go to Hawaii data sets for that because Hawaii is not like the continental U.S. in its rainfall. It's a Pacific Ocean dominated system with geographic impacts, which we discussed in previous lectures. When we select the data that we're going to download for a climate scenario, we can identify the type of data we want, precipitation for 15 minutes, for example. We can select the date, the range, 1970 to 2014. That's a long period of record. That's 44 years of record at 15-minute intervals. Think about that. We can identify our location by cities, by geographic area, by longitude, latitude. Here I use Fayetteville, Arkansas, and I get Fayetteville, Arkansas data here. I get Fayetteville, North Carolina, which is not here, don't be confused, or Fayetteville, Alabama. But we also have rain gauges here in Camden, Harrison, Hot Springs, Russellville, El Dorado, Forest City. All these rain gauges have data, and you can select those data and add them to your card and download those as CSV files for analysis. So the hydrologist has unparalleled access to data now. This is relatively new. Back in my day, we didn't have this kind of information. It was hard to get, but I digress. I provided for you already a 10-year data interval from 2000 to 2009 inclusive of rainfall from the Fayetteville weather station, which is located on the University of Arkansas Cooperative or the Division of Agriculture farm for the USGS weather station. We have the latitude and longitude of the location and its elevation, 387.1 feet above mean sea level. And we have two types of data in columns. We have the volume of precipitation calculated by weight in the Q gauge. This is what the tipping bucket is sensing, and that's converted to the amount of precipitation, in this case is in inches, at 15-minute periods. So you can see we have small increments of increase of rain for this particular storm event, relatively low increments of rain. This is a very mild rainfall event. And then we have these odd numbers, minus 9999s, and we have plus 9999s in the system. These are errors in measurement. You can hit Control H to find and replace error numbers in your columns and you can replace those with 0.0001s, which is preferred, or with 0. Zeros are tricky numbers because you really can't ever say it's 0, but you can certainly say it's close enough to 0 to be irrelevant. And usually 0.0001 would be a good replacement for those data. We can also go to the NASA Atlas 14 point precipitation frequency estimator using the same sort of mapping system at the same web page, and we can download the return periods and their PDS-based precipitation frequency estimates with their 90% confidence intervals, which we discussed in the previous lectures, across everything from a 5-minute duration to a 60-day, 2-month duration. And you can download these data too in an Excel file. Incredibly robust data that you have access to. The data are on a CSV file, comma delimited data file, and you can import those directly into Excel and then save them as Excel files. Again, this is the frequency estimates that I just downloaded for this site. The appropriate NOAA Atlas 14 Volume 9 Version 2 data or references are included. Gives us latitude and longitude, elevation 1,270 feet. So the previous elevation that I said 370 was in meters, not in feet, clearly. You got to be careful about that. I get tripped up by that from time to time too. So Fayetteville, Arkansas is at 1,100 to 1,200 feet elevation, give or take a hill or two. The averaging precipitation across area is the key. It's difficult. The methods I provided for you in the NOAA Atlas 14 provides you the methods for doing this. My key is to give you information to continue to learn well beyond this class, and this is one method. Now these volumes, these frequency atlases of the United States are divided by region. So volume 9 is the southeastern states, Alabama, Arkansas, Florida, Georgia, Louisiana, Mississippi. If you're working in other areas, you have to download different volumes if you're working in other areas of the U.S. or its territories. Rain falls on a watershed. The watershed accumulates the water. It's allocated to the water budget. If you don't have precipitation data specifically for your location, but data are available for nearby, that's the case too, you have to use an area averaging method to generate data for your site. There are 3 primary methods for area weighting precipitation data. The arithmetic average, which is the easiest but most restrictive, where you just average the rainfall at every increment across all the weather stations. The Thiessen polygon method, which is objective but needs a large network of rain gauges, or the isohyoidal method, which is the most accurate, but it's the hardest. It requires some expertise and judgment. Let's talk about those real quick. The arithmetic average for a specific period across all sites within an area is just simply that. You average all the data. So if you have 3 sites, you add them up and divide by 3 for each event, each observation. But it can introduce bias into analysis. If the difference in rainfall for a given event is more than 10% across these sites, this method is going to have too much bias. You shouldn't use it. If the difference in rainfall for a given event is more than, well, that's redundant. Also, if there's geographic differences across the site, you probably shouldn't use this method. So the Thiessen polygon method is named after an engineer, Thiessen, who developed this in the early 20th century, where you simply take the watershed and all your rain gauges in the watershed, and you divide all the areas into polygons, and you do an area weighting for each polygon. So here we have 9 rain gauges, and we have, say, 15-minute intervals, and they're weighted by the fraction of the catchment area represented by the gauge. And then the weighted and precipitation area is summed. So the aerial precipitation R bar is given by the sum of R at a given site, 6, for example, over the area of 6 divided by the total area. Area of 6 divided by the total area is just the proportion that area 6 represents of the total area, or area 1 of the total area. Let's say this is 10 hectares. The whole thing's 100 hectares. So the A1 over A is 0.1. So you would take R1 times 0.1. Notice that this rain gauge is outside the area, but still within the watershed, this area is captured. So the area proportions are called the Thiessen coefficients. These are not that complicated to build. You draw a straight line between each of the rain gauges, and then you go to the midpoint between that straight line, the halfway point. You draw these lines like this. See, draw a line between these three. Then you'd go to the midpoint between them, and you draw these other lines. Halfway between these two, you draw a perpendicular line. Halfway between these two, you draw a perpendicular line. Halfway between these two, you draw a perpendicular line. And so it goes until you end up with all these divided areas. That's the way this method works. It's a very graphically familiar and intuitive way. Now, how do you then calculate the areas of these systems? Back before we had GIS, there were a number of ways. You would plot these on gridded paper and count the number of grids within each box. Another way that I've actually used is you plot these on a piece of paper and you photocopy that paper. You cut out the whole area, you weigh it, and then you cut out each of the boxes and you weigh each of these boxes and you assume that the density of the paper is equal, and you end up with a weight-based extrapolation of area. You don't have to do any of that these days. As I just indicated, you can just look this up. But it's important to know how this was done. Now, the isohedral method, which means same rainfall method, you would take all these rain gauges and you would say, all right, I'm going to use in millimeters 20, 30, 40, 50 millimeter dividers across this system and look at all the rain gauges, and I'm going to estimate areas where you had the same rainfall. And I'm going to draw these lines. And you can do this with geographic statistics. Most professionals used to do this just sort of manually, just extrapolating. So between this side and this side, you're at 43 and 35. So this line of 40 is, you take the difference, and the line of 40 over this is a difference of 8. So, and then the difference between 35 and 40 is 5. So 5/8 the way between here and here, you put a box. And then you do the same thing all the way around. You draw these little X's and you interpolate lines around them. So that's the way you draw isohedral areas. And then you do the same thing. You simply do an area weighting based upon the isohedral areas times the amount of rainfall in that area, just like we did with the Thesan polygons. All fairly straightforward. This is what USGS is doing for you automatically using very good geostatistics. I hate to say you don't need to know how to do this, but you don't need to know how to do this manually anymore because you have it automatically. But what happens if you're working in an area where you don't have this sort of robust data set? Then you need to know how to do this, and you can look this back up. You know there's a way to do it. That's why we're not having a homework assignment with these assignments, because it smacks of busy work. We need to know the characteristics of rainfall events, not just the sort of overall rainfall totals to design a process or facility. Location matters. We can look at Aden versus Singapore. Look at the difference of rainfall. These are 12-month averages, so each of these little boxes is monthly average rainfall. What you see is in Singapore is you have a wet season between January and December, the winter wet season in Singapore. And Aden, you have an arid system with virtually no rain. In Abadan, you have a bimodal distribution of wet seasons, which is kind of what we have in Fayetteville. In Oxford, England, it's just wet all the time. In New Delhi, you have monsoon season. In Zinder, you have a monsoon season. So getting to know these patterns for your area is important. We've already discussed, and when we talked about meteorological drivers of precipitation, the kind of rainfall events we get in different zones. But here's a review as well. So in equatorial zones, you typically have 2 seasons, maximum seasons. Tropical zones, you have summer rain, winter dry. With the tropics of Cancer and Capricorn, you have 2 summer rainfall events. And so that's the sort of purpose of this table, which you can certainly review. And this was in 1958. 60 years later, it hasn't changed much. It is changing, but not the patterns. The intensities are changing. Precipitation characteristics follow a number of distributions. If we look at daily precipitation, it's not unusual to have a J distribution. It starts raining real hard, then it drops off to nearly nothing. And over numbers of days, if we look at numbers of days of rainfall, daily rainfall, You have a whole bunch of wet days and then not very many more. If you look at monthly rainfall, you generally have number of months of rain, amount of rain in months, usually have the seasonal effects showing up. And if you look at annual precipitation, you see the graphs we just saw earlier. So you can see that we have a J distribution, a log normal distribution, and a normal distribution, depending on the time frame that you're looking at in terms of number of days, number of months, number of years, and the type of rainfall you get in millimeters. Engineers have historically used the probable maximum precipitation amount. For any given event, it's the conceptual maximum rainfall for a location. Well, there's a finite limit to the amount of rain. It's a finite limited amount of rain that can fall during a specific event. So as a design engineer, you say, well, the PMP is the thing you design for. Remember we talked about risk assessment and how you predict that based on return period. The concept of PMP, to which no return period or recurrence interval can be attached, is attractive to the engineer because it just says, all right, we're safe here. If we design for this amount, it's not going to exceed that. It's the depth of precipitation for which a given area and duration can be reached but not exceeded under known meteorological conditions. When a value of PMP is required for a specific project, it is usual to estimate it by several methods and then make an engineering judgment on the value to be used. Now, we call this best professional judgment. And in most cases, best professional judgment equals wild ass guess. BPJ equals WAG, or at best a scientific wild ass guess, a swag. Engineers have been swagging it for decades, for a century. The statistical representation, it's not the actual calculation, but a way to estimate PMP, is expressed as Rmax equals some A regional constant times D, the maximum duration, in hours to the 0.48. The average for A in the continental United States is 16.4 inches. If we look at a 6 hour, 6 square mile, or 25 square kilometer, 5 kilometer by 5 kilometer PMP, we can see what those are in inches. We can multiply by 25.4 to get millimeters. So in Fayetteville, Arkansas, it's about 30 inches. So, right, you should never get more than 30 inches. Or down around the Gulf Coast, you should never get more than 32 inches. That's the historic thinking. And the engineers have been using this for a century. We think about Houston and the Gulf Coast. Let's think about what's happening now. Remember the criteria for our ability to predict the future. One of the conditions is the conditions that led to all of our data up to this point haven't changed. We know that the climate is changing. So an Rmax for Houston for a 6 hour event was 32 inches. Kunkel analyzed PMPs in the context of climate change. They found that for a high energy assumption of climate change, mean and maximum water vapor concentrations result in increased maximum values for the continental U.S. of approximately 20 to 30% in the next 40 to 60 years. They concluded that the most scientifically sound projection is that PMP values will increase in the future due to higher levels of atmospheric moisture content and consequent higher levels of moisture transport in storms. So as a young engineer, as you go into practice, and your older engineers, senior engineers tell you, well, the PMP for this area is 32 inches. You need to be skeptical, and you need to challenge that and say, based upon what? Because the evidence today is clear that in the next 40 years, that's going to be at least 30% higher. 30% higher would put it in the 40-inch range. Evidence of that, Houston, Texas, Hurricane Harvey. My daughter happened to live right here in League City at the center of this. Now, since her dad's a good hydrologist, she lived in an apartment complex that was on high ground, relatively high ground in the bayou country south of Houston. She didn't flood. Her parking lot accumulated a few inches, but she had friends who all lived around Johnson Space Center who had to move in with her for a couple of weeks because of flooding. Their apartments had a foot, 2 feet of water in it. The 5-day point rainfall events in this area exceeded 50 inches. And most of that occurred over a 6-8 hour period. 50 inches. Not 32 inches, 50 inches. And these are 5-6 day totals, but most of it occurred over the first 5 to 6 hours. And then it just kept raining, drizzling after that. So you have lots of data. Again, I'd like you to look at these sites, get to know them, get to know the data, explore them. I'm not here to hold your hand. I'm here to show you the way. You have to walk the path. So take a look at these sites, understand what data are available to you. If you have questions about the data, bring them up and we can talk about them. But most importantly, it is upon you to understand what data are available and where they are from. That is the way you become a competent professional. That is the way you lead your teams in practice. That concludes this lecture on precipitation. Thank you.